Hello everyone. So with this lesson, we're going to start talking about vectors. So in your warm-up, we're going to be finding the distance between 2 points, and then we're going to be looking for a missing angle. So I went ahead and just left these filled in just because I want you guys to kind of take some time, read through it, write it down, or practice it yourself. These are really just kind of prior skills that you should already know, but I wanted to kind of bring these skills back as we segue into this kind of idea. So these different topics, from distance formula and finding an angle of a triangle, we're going to use those skills when we venture into vectors. So kind of looking forward, so we need to first determine the difference between what we call a scalar and what we call a vector. So a scalar is only going to describe a quantity of a magnitude. So in this case, we can talk about mass, we can talk about temperature, we can talk about speed, or if we want to write it in terms of context of a problem, we could even say like 30 kilograms. Now, down here, I know a lot of people kind of mix up that speed is actually just a scalar, it's not a magnitude. So for example, if I'm on a highway going, say, 60 miles an hour, 60 miles an hour is only telling you the actual magnitude. It's not actually telling you a direction that we're going in. So I might be going 60 miles an hour north, I might be going 60 miles an hour south, I might be going northeast or whatever. So whenever we talk about speed, it's only going to be a scalar, not necessarily a magnitude. So when I go, or not a vector, sorry. Now when I look over at a vector, it's similar, but we're gonna add in a direction as in addition to having the magnitude. So with a vector, your examples are going to include items such as force, displacement, acceleration, or even velocity. So the big difference between, say, speed and velocity, speed only has the magnitude, whereas a velocity is going to have the magnitude with a direction. So if I say I'm going 30 miles an hour, that would just be a speed. But if I am going to tell you I'm going 30 miles an hour northbound, that becomes a vector, which would then become velocity. So as we move into the notation of vectors, so when we're talking about magnitude, we're going to be using what look like the absolute value brackets, not really brackets, but bars. Now, I've seen the magnitude be written with a double set of absolute value bars, but I've also seen the magnitude written with a single set. I'm not going to stress whether it's a single or a double set. As long as you can include the absolute value bars, honestly, I'm happy. And then with the direction is going to be the angle that the vector makes with the positive x-axis. So more specifically, we're also going to be bringing back reference angles. So reference angles, and then we're also going to be looking at angles in standard position. And then with standard form, it's where it's going to begin at the origin. So when we're talking about the standard form of a vector, we want the initial point where it starts to actually be at the origin, not anywhere else on the graph. So looking at the components of a vector, we're going to have what we call the initial point, which is going to be where it starts. We have a terminal point, which is the ending point, which we can also refer to as the tail. And then we have the two components of a vector. So we have the x component, which represents the horizontal distance. Then we have the y component, which is going to represent your vertical distance. And then with the magnitude, that's going to be the length of the vector. So this is where you may need to do distance formula. And then with direction, this is more specifically, we're going to be measuring it in degrees. So you got to make sure that you're going to be in degree mode on your calculator. Now, the direction is going to include the direction if it is applicable. So meaning, if I'm going to say it's going 30 degrees, I want to say 30 degrees going east or going north if possible, if we have that context in the problem. And then with the direction, this is where we're going to be doing your inverse trig. But more specifically, we're going to be using inverse tangent. So I have a diagram over here with all the different parts of a vector labeled. That way you can kind of put your terms to a visual of what we're looking for. Now, as we move into the direction, or rather, we're going to look at what we call component form. Now, component form it's written like a coordinate, but in terms of a vector. So component form is going to be written with what looks like these inequality signs on both sides of your sign. So, or coordinate rather. So instead of writing parentheses, we're going to have these what look like inequality signs on the sides. Now those inequality signs, I actually informally I call them pointheses, just because I don't want to call them parentheses, but I don't want to call them inequality signs because that's not what they are. So I just kind of came up with my own little name for it. So parentheses is what I use to describe these values, or describe these signs. So as we move into the components, now we're going to also look at components of directions. So over here, we're going to look at how you would graph a vector going in the direction north of east. So what you're going to start with is I am actually going to be going east, but I want to go north of east. So meaning I'm going to start going east, but then I'm going to go a little bit north. So this would be my vector right here. And then your angle, which is going to be your theta value right here. That's going to be the angle that we're going to be measuring. So in standard position, remember standard position is going to be measuring from the positive x-axis, and we're going to go counterclockwise however however many degrees it goes counterclockwise. So in this case, because we're just north of east, our angle in standard position is just whatever that theta value is. And then if I have an angle that's going south of west, well, that tells me I'm going to go west, and then I'm going to go a little bit below to represent south. So that would be this angle right here, since we're in relation to the x-axis. Now, if I want to measure this angle in standard position, remember, we need to start over on the positive x-axis, and we're going to go all the way counterclockwise. So then this would be our angle in standard position. So your standard position angle would be your theta value, and then plus 2 full quadrants, which means we're going to add 180 degrees to that angle to find it in standard position. And then to right south of west, you're just going to abbreviate. So we're going to do S of W. So S of W. So now I'm going to invite you to try 3 and 4 on your own. So with number 3, so now I want to go west of north. So you're going to start going north. You're going to start with whatever direction is second, and then you're going to use the direction of the first word. So I'm going to go west, which is going to be a little bit to the left. So what that tells me is that my angle is going to be right here. I really should actually start with writing it. So we're going to abbreviate. So W of N would be west of north. So now I need to write it in standard position. So standard position is going to be from the positive x-axis going counterclockwise. So we're going to have 1 full quadrant, which is going to be 90 degrees, and then plus whatever we went in terms of theta. So that means my x value here, standard position, is going to be my theta value plus 1 full quadrant, which is 90 degrees. And then if I want to do east of south, so east of south, once again, we're going to do E of S. So I'm going to start going south, and then I'm going to go to the east. Sorry, y'all. So my angle here in question, I need to do my arrow, there we go. So my angle here in question would be right here. So this would be my theta. But then in standard position, I'm going to start positive x-axis and go all the way around. So notice how I went through 1, 2, 3 full quadrants, and then I also need to include that theta. So that means because I went 3 full quadrants and theta, I'm going to do theta plus 270 degrees. Now, if you look at this diagram I have over here on the right side, I have every possible cardinal direction that we're going to be talking about. So all 8 of these directions are what we're going to be referencing at some point. So I only did 4 of them out of the 8, but hopefully you can kind of figure out the standard positions and everything else of the other 4 directions. All right, now we're going to move on to component form. So component form, when we're looking for the magnitude and direction, we're looking specifically at using Pythagorean theorem, and we're going to apply what we already have. So when I do Pythagorean theorem, that's going to give me the magnitude. And then if I want to find the angle or the direction, which is going to be right here, then notice how I need to do inverse tangent since we're doing the opposite and then the adjacent. So we don't necessarily need sine and cosine for most of these problems, if not all of them. We might use sine and cosine very sparingly, but it's going to be very few and far between. And then when we're given the magnitude and direction and we want to find the x and the y component, then we're actually going to be doing our sine and cosine ratios and then solving it for our x and our y values. So if I have cosine, that's going to be the adjacent over the hypotenuse, which is x over the magnitude. And then if I solve it for x, I'm going to multiply the magnitude on both sides, which means we're going to have the magnitude times cosine of that value for my x component. And then same idea for sine for the y component. Sine would be the opposite over the hypotenuse. So if I solve it for y, that's going to be the magnitude times sine of that angle. So this is where we're going to be using sine and cosine. All right, now we're going to kind of put it all together. So we want to sketch the vector given the magnitude and the direction, and then we're going to write each vector in component form. So we have a vector v with a magnitude of 2 centimeters and a direction of 24 degrees north of east. So north of east tells me I'm going to go in the direction of east, and then I'm going to go north. And then the angle that's formed is going to be 24 degrees. And then I also know, based on the magnitude that they give us, that this is going to be 2 centimeters. So I want to be able to find the vector in component form. So in component form, so I know my x value is going to be equal to the magnitude times cosine of that angle. And I know the y value, or the y component, is going to be the magnitude times sine of that angle. So what I'm going to do is I'm going to plug in. So we're going to have the x component is equal to the magnitude, which we know is 2, and then cosine of 24. And then over here for the y component, I'm going to do the magnitude, which is 2, times sine of my angle, which is 24. And then when you get here, I can write my component form in exact form, or I can write it in approximate form. So exact form is if I just leave it in terms of sine and cosine. So my coordinate, using parentheses here, would be 2 cosine 24, comma, 2 sine 24. And then if I want the approximate, this is where you're going to actually plug in these values on your calculator. So make sure that your calculator is in degree mode, because if you are in radian mode, you will get all the wrong answers before you even start. So when I plug in 2 cosine 24, so yes, I am in degree mode. So that's going to give me 1.827. And then comma, now I want to do 2 sine of 24, and that's going to give me 0.813. So depending on the context of the question, we may want the exact, we may want the approximate, but in this case, both of those could qualify to be your answer, depending on what we're looking for. So now looking over at number 2, so now we're going to be given a vector with magnitude of 5 inches in a direction 80 degrees south of west. So to start off, I have a vector that's going in the direction of west, but then I want to go south. So 80 degrees, so it's going to be pretty close to 270. It's actually going to be further than that. It's probably going to be about down here, actually. So I know that this angle right here is going to be 80 degrees. So whenever we're plugging in for component form, you need to plug in standard position angles. So if I plug in the 80 degrees, then that's going to be describing a vector that's going up here. This angle would be 80 degrees. But that's not what we want. We want this full angle going all the way around. So whenever you're doing standard position, so I know my standard position angle is going to be 2 full quadrants here, which means I'm going to do 180 plus my theta value. So that means I'm going to do 180 plus 80, which means my standard position angle here is going to be 260 degrees. So 260 is actually the angle I'm going to plug in for component form. So now that I'm ready to do that, so I'm going to do x is going to be equal to the magnitude, which is 5 inches, which I did not write over here. Whoops. So 5 inches, there we go. So the magnitude, which is 5, then cosine of 260. And then for the y component, now we're going to do 5 times sine of 260. So if I want the exact form for component form, then I'd do 5 cosine 260, and parentheses, not parentheses, comma, 5 sine of 260. So that's your exact form. But then when I do approximate form, I'm going to plug in, so 5 cosine 260, which is going to give me a negative 0.868. And then 5 sine of 260, which is going to give me a negative 4.924. So depending on the type of answer we want, that would be your value. So I would definitely recommend trying number 3 on your own, and then we'll see how you do. All right, so with vector v magnitude of 10 miles and a direction of 10 degrees east of south. So I want just 10 degrees east of south, so it's going to be a little bit of a teeny tiny space. So this would just be 10 degrees, and then with a magnitude of 10 miles. So for my actual angle and standard position, so we're going to go 3 full quadrants plus that 10 degrees. So that 3 full quadrants that we did is going to be equal to 270 degrees, and then plus the 10 degrees that we did east of south. So that means in standard position, our angle here is going to be 280 degrees. So when I write my component form, so we're going to do the magnitude, then cosine of 280, and then my y value will be 10 sine of 280. So in exact form for component form, so we're going to have 10 cosine 280, comma, 10 sine 280. So that is your exact. Now I need to plug in, so 10 cosine 280, which is going to give me 1.736. And then 10 sine of 280 should give you negative 9.848. There we go. So with this next section, now we're going to be given different vectors on a grid, and then what we want to do is we're going to write the vectors in component form, and then determine the magnitude and the direction. So the magnitude is going to be doing essentially Pythagorean theorem, which is finding the distance, which is where the distance formula comes from. And then we're going to do the direction, which is where we're going to be doing inverse tangent. So in order to find the actual component of the vector, what we need to do is we actually need to find the terminal side, which tells you we're going to do the side with the arrow. And then we're going to subtract where it starts. So you could say like where the arrow is, or you could even say like where it ends. So the ending minus the starting, however you want to phrase it. But in technical terms, it would be the terminal minus the initial side. So I'm looking to do a couple of these. I'm not going to do all of these, otherwise this video would be 20,000 hours long. So we're going to start with just vector A. So if I look for vector A on my little map here, so I need to find the coordinates. So the initial side of vector A would be the coordinates of -7, +1. And then the coordinate of my terminal side, which is where it's going to end, is going to be -6, 3. So looking down here, if I want to find component form, what I need to do first is I'm going to do the distance between these values. So I'm going to do x2 minus x1 and then y2 minus y1. But more specifically, I'm going to do the terminal minus the initial. So when I plug in, so my terminal side is going to be -6 minus -7. And yes, the order does matter in this case. You have to do the terminal minus the initial. And then for the y values, then I'm going to do 3 minus 1. So what's going to happen here is we're going to have -6 minus a negative, so that's going to turn into addition. And then this is going to give us -6 plus 7, which is going to give us 1, 3 minus 1, which is going to be 2. So right here, this would be our angle, or not angle, our vector in component form. But now I still need to find the magnitude and the direction. So the magnitude is where I'm going to do essentially a Pythagorean theorem. So I'm going to do the square root of the x component squared, which is going to be 1 squared, plus the y component squared, which is going to be 2 squared. So when I simplify this, so we're going to have a square root of 1 squared, which is 1, plus 2 squared, which is 4, which is going to be square root of 5. So that would be your magnitude. Now we need to find the direction. So in order to find the direction, we're going to do inverse tangent. So I'm going to do inverse tangent of the y component over the x component. So the y component, which would be 2 over 1, which in this case is just going to be inverse tangent of 2. And then, no, we can't evaluate that from the unit circle, but with these values, we are going to be using calculators. So I want inverse tangent of 2, which is going to give me a degree value of 63.435 degrees. So now we also have our magnitude and we have our direction. Now this is going to be measured in standard form, which means I don't really need to do any like north of east or anything like that, so I can just leave it like that. Okay, so I'm going to give you guys about a minute or so. I'm going to let you guys try number 7. I just chose a random one. So you're going to do vector D. All right, so with vector D, so I have -1, 1 for the initial side, and then the terminal side, we're going to be given 4, 2. So I need to start writing component form. So component form means I'm doing x, y in these parentheses, and then I'm going to do the terminal side minus the initial side. So for the x component, I need to do 4 minus -1. And then for the y component, I need to do 2 minus 1. So when I rewrite, so this is going to give us 4 plus 1, which is going to be 5, and then 2 minus 1, which is going to give you just 1. So for the magnitude, so I'm going to do the square root of the x component squared plus the y component squared. So that's going to give me square root of 25 plus 1, which is going to be the square root of 26. So if we want the decimal form of it, which we may want just the initial or the exact form. But if we want the decimal, then you can plug it in, so it'd be 5.099. And then if I need to find the direction, which you will, we're going to do inverse tangent of the y component over the x component. So inverse tangent of a fifth, which is going to give you 11.3099. So show you how we need to round. So because of this 9, I need to round this up, which means this 1, or nope, this 0 will now become 1. So my actual simplified, or rounded answer rather, will be 11.31 degrees. All right, now moving on to the next section. So you want to sketch the given vector, and then you want to find the corresponding direction and magnitude. So really it's the same as what we just did up here. The only difference is now we're just going to be given the component form. But with the component form, we don't know necessarily, well, yes, we do actually. We're going to be looking at the quadrant that this vector is in, which means if your vector falls into quadrant 2 or 3 or even 4, we're going to have to adjust the angle. So if you are in quadrant 2 or quadrant 3, we are going to need to add 180 degrees because of the restriction to inverse tangent. So remember, inverse tangent is restricted to negative pi over 2 to positive pi over 2. So when I look at my quadrants, so for inverse tangent, what this is telling us is I can be from negative pi over 2 to positive pi over 2. So I can only work in quadrants 1 and 4, so I can't be in quadrant 2 or quadrant 3. So if my value is actually going to be in quadrant 2, for example, if I need to be over here, then that means I need to find the quadrant 4 value, and then I'm going to add 180 degrees to put it in quadrant 2. And then conversely, if I'm in quadrant 3, what's going to happen is I need to find the quadrant 1 value, and then I'm going to add 180 degrees to put it in quadrant 3. Whoops. No, come back. And then lastly, if I'm in quadrant 4, this is going to give me a negative angle because this is the angle that it's going to give me on the calculator. But what we actually need is a positive angle, which means I need to find a coterminal. So I need to come all the way around, and we're going to find the positive version of this angle. So in order to do that, we're going to do this negative angle, and then we're going to add 360 to make it a positive angle. That way it still represents the same thing. So that's why we're going to have these specific rules. Okay, listen here. So starting off, I am looking at number 10. So we have the vector 3, 4, which if you think about the coordinate grid, 3, 4, it's positive, positive, so that's going to be in quadrant 1. So we're not going to have to do anything special or fancy to this angle, or this vector rather. So I'm going to start with finding the magnitude. So the magnitude is just going to be Pythagorean theorem. So I'm going to do square root of 3 squared plus 4 squared. If you know your Pythagorean triples, this would just be 5. And then I need to do my angle. Whoops, forgot my theta. So I'm going to do the y component over the x component. And then plug in, so inverse tangent of 4 over 3, which is going to give me 53.13 degrees. So we have our magnitude, and then we have our direction. Now, this is going to be measuring it in standard form, which we also need to sketch. I knew I was forgetting something. So if I do 3, 4, it's going to be about like this, which means our magnitude here would be 5, and then the angle that we just found is going to be 53.13. So more specifically, if I wanted to give a direction, then this would be north of east. Now, here's a little trick question, not really a trick question, but here's a little extension for you. What if I told you I wanted you to find the angle in terms of east of north? What would that angle be then? So if I want east of north, that means I want this angle. So if I want to find that angle, that means I would need to do 90 degrees minus that angle that we just got. So I could do 90 minus, and that would be 36.87 after you round. And then that would be east of north. So you've also got to pay attention to the type of angle that we want, whether we want it like north of east or east of north, or if there's a certain context. So now looking at 11, so let me actually start with the sketch first. So -5, 12, that's going to put you in quadrant 2. So quadrant 2, automatically what that tells me is I'm going to need to add 180 to my angle. So when I draw my vector, so -5, 12, I missed. It's going to be like that. So what I want is when I measure my angle in standard position, this is what it's going to measure. So first we're going to find the magnitude. So it's going to be square root -5 squared plus 12 squared. So once again, if you know your Pythagorean triples, that would give you 13. Which they're not always going to be Pythagorean triples. And now we need to find our angle. So our angle here, now keep in mind, when tangent is negative here, so if I do my y over my x, that would be negative. That means the angle that it's going to give us on the calculator is actually going to give us the quadrant 4 angle. So on the calculator, this is what it's going to give us. So when I plug in, so I want inverse tangent of 12 over -5 or -12 over 5, whichever one. So when I plug in, so I'm going to get -67.38 degrees. So that is what is giving us right here. So 67.38, I'll do the 01, why not? So that's why when we're in quadrant 2, we need to add 180 so that we can actually put it back over here. So really, when I add 180, my angle is actually going to be 112.61986. So that would just be 112.62. So that would be this angle, which really I should have done this in green. Stay with my colors. There we go. Okay, so in standard position, it's 112. Now, here's the thing. I have a couple different angles that I could also find in terms of context. I could find this angle right here, which I'll say theta 1, and then this angle right here would be west of north. But I could also technically find this angle down here, which I'll call theta 2, and then this would be north of west. So there's a whole bunch of different ways that we potentially could classify this angle. So it really just depends. So let's say we want to find the west of north. So if I want to find the west of north, what that means is I want to keep all the angle values in quadrant 2, but I want to eliminate all the quadrant 1 values. So theta 1, what that's going to be equal to is going to be my theta value minus 90. So I'm going to do 112 minus 90, which is going to give me 22.6198, which would be 22.62 degrees west of north. So that could be one way that we write our angle. And then the next way, if I do theta 2, Then because I want this full angle here, I essentially want to do 180 degrees minus this theta value. So I'm going to do 180 minus theta. Which is going to give us 67.38 after rounding. And then that would be north of west. So if I want the angle in standard position, then you would tell me the 112.62. If I want the west of north or north of west, then you would give me either one of those angles. So I know I'm not very clear in the directions on which direction I find. Usually if I don't state the direction, then I'm going to want it in standard position, which means for this angle, I would want the 112. But I'm going to go ahead and kind of extend it more just so I can give you kind of more practice and more ideas of how we could expect you to find these angles. So with that, I'm going to invite you to pause here and actually try 12 and 13 on your own. So with number 12, I see that I have a negative negative, which tells me that that's going to put us in quadrant 3. So in quadrant 3, that means I'm going to need to add 180 degrees to my angle to put it in standard position. So starting off, we're going to do the magnitude, which I really should have come up with some better values because these are all Pythagorean triples. So, nope, what am I doing? So we're going to have negative 5 squared plus negative 12 squared. And then once again, this Pythagorean triple, that would just give you 13. So then we need to find our angle, which I also need to sketch it. Whoops. So inverse tangent of negative 12 over negative 5, which is going to come out to just be positive 12 over 5. Okay, let me go ahead and stop here. Let's go ahead and sketch. Give you an idea of what we're working with. So my angle or my vector in question would look something like this. But when I do my angle, because it's going to be positive, it's actually going to give me the quadrant 1 vector, or the quadrant 1 angle. So this is what it's actually going to give us on the calculator. So what I really am going to need is the standard position angle. That's what we're going to add 180 and get. So when I do my inverse tangent, it's going to give me 12 over 5, or inverse tangent of 12 over 5, which is going to give me 67.38. And then I need to add 180 degrees to put it in quadrant 3, which means my angle is actually going to be 247.38 degrees. So 38, I'll go ahead and do 01. No, I'm not. So in standard position, this is what our angle is. But depending on the context of the question, I might ask you to find south of west, or I could even tell you to find west of south. So depending on context of the question, you may need to find those angles as well. So if I want to find theta 1, so that means I need to do 2 quadrants. I need to eliminate 2 quadrants from my value, which means I need to do my angle minus 180 degrees. So I do 247 point, that value minus 180, which is going to give me 67.38 degrees. And then that's going to be south of west. But then if I want to find angle, or theta 2, so what this means is I need to actually do all 3 of these quadrants, which is going to be 270, and then I'm going to subtract the standard position angle. So I'm going to do 270 minus the standard position, which is going to be your theta. So 270 minus 247.38013505. I'm going to plug in the whole thing. And then that's going to give us 22.62 degrees. And then that would be west of south. And then last but not least, we're going to go ahead and do 13. Let me actually start with the sketch this time, which is what I'm supposed to do. All right, so we have the vector 6, -8, which 6, -8 is going to put us down here in quadrant 4. So because we are in quadrant 4, what that tells us is our final angle and standard position, we're going to have to add 360. So when I do that standard position angle, that's going to give me this full angle right here. So we're going to start with the magnitude. I believe this will be a perfect square. Yeah, it's another Pythagorean triple. So we're going to do 6 squared plus a -8 squared, which that's going to be square root 36 plus 64, which is going to be square root of 100, which is 10. So now I need to find the angle in question. So let's do it in green. So my theta value is going to be inverse tangent of my y value over my x value, so -8 over 6, which this is going to simplify. So inverse tangent of -4 over 3. So when I plug this in, so that's going to give me -53.13 degrees. But then when I add the 360 to put it in standard position, that means my actual angle here in question is going to be 306.87 degrees after rounding. So here's my standard position angle. Now, because I'm in quadrant 4, that means the two other potential directions I could ask you, which I'll do theta 1 and a theta 2 again. Here, let's switch these so I can go in order for standard position. So theta 1 will be in orange, and then theta 2 will be in pink. So for theta 1 here, this is going to be east of south. And then here in pink, this would be south of east. That's a weird E. Close enough. So let's say we want to find theta 1. So if I want to find theta 1, that means I'm going to do my full angle, and then I want to eliminate 3 quadrants, which means I need to get rid of 270 degrees. So I'm going to do my angle minus 270. So that means I'm going to do 306 minus 270, which is going to give me 36.87 degrees. And then that would be east of south. And then for theta 2, then that means I need to do a full rotation 360 minus the actual angle. So 360 minus theta. So I'm going to do 360 minus 306.8698976, which is going to give me 53.13 after rounding. And then that would give me south of east. So once again, just to reiterate, we're going to majority of the time want the standard position angle. I just found these other values with those cardinal directions just in case, but I'd rather give y'all too much information than not enough. But hopefully this wasn't too terrible. Have fun, make good choices. Bye-bye.